So on the previous episode, we solved the Kronig Penney model in the real space, and as you realized, and as you know from the screen and from the slide ahead of you, that we saw that band gaps emerge in this description. And now what we will do in what follows is that we will repeat solving the Kronig Penney model, but now in the reciprocal space using the central equation that we have discovered in the Bloch theorem lecture. So we have now solved the Kronig Penney model. We know that how the solutions look like when we have this periodic square potential that forms the core of the Kronig Penney model. And we have solved the system in the real space. So essentially we just solved the below Schrödinger equation, and I do not go into the details of this one-dimensional Schrödinger equation anymore, but we just have covered it many times, and we have already in the previous lecture we discovered what are the solutions. And now, as I promised, we will go on and solve the problem in the reciprocal space description using the central equation. And the central equation was of this form, where we have the kinetic energy term. So we have the h bar squared times k squared divided by 2 times me minus e times the coefficient ck. So this is the Fourier coefficient associated with the wave function. So when we decompose the periodic wave function into the Fourier series description, these will be the associated coefficients. And then we have also the potential term, and there we are summing over the reciprocal lattice vectors g's. And then we have the associated Fourier coefficients of our lattice periodic potential function u, and these will be the Fourier coefficients of the potential function. And then we have also the Fourier coefficients associated with the wave function, so ck's. And this was equal to 0, and this was known as the central equation. And unlike above Schrödinger equation, which is a differential equation, this is an algebraic equation, so essentially this is slightly simpler to solve. And in principle, we can even, if we are lucky, and we will be, we can like linearize this, and we can form a matrix equation, and we can solve that. And this is also nice because in the like a generalization, if you would need to go into more complicated potentials, this central equation approach is way easier in terms of generalizing the math. And what we will get out as a solution, well, we will get a dispersion relation out. And this dispersion relation is essentially also known as the energy band structure. And this structure will, of course, be of the same form as before. So importantly now, unlike in the free electron model, in the nearly free electron model, we actually have emergence of those band gaps in our description. And the nice thing, as I already mentioned, with the central equation approach and solving the Schrödinger equation in the reciprocal space, is that now this approach could be used if we would have more complicated potential forms. So for example, if we would need to describe a 3-dimensional system, then I recommend you to consider solving it in here, because we know how to take Fourier transforms out of also 3-dimensional functions, so that we don't need to be restricted to a 1D case anymore. And how do we proceed is that we start writing the potential u as a Fourier series, and please note we are keeping the dimensionality as a 1-dimensional case out of simplicity and conceptual clarity. And now we just write the potential using the Fourier series description. So ux must be of the form 2 times sigma summation over the reciprocal lattice vectors, and now here over the positive reciprocal lattice vectors of ug, the Fourier coefficient associated with the periodic lattice, times cosine of gx. And here the reciprocal lattice vector g, of course it's now a scalar because we're treating a 1D case. That is of course 2 pi over the lattice constant, and in our case that would be the a plus b, where b was the width of the barrier. And as earlier, we simplified our math to have b equals 0 case. This also simplifies our reciprocal lattice vector here, so that b equals 0 in our treatment as earlier we did so already. And this, of course, is an equation that is providing us a general form for the potential. Let's now go on and let's describe this potential, the periodic square well in real space, and how it would look like is that essentially this would be a capital A times small a, and we would sum over Dirac delta functions of x minus MAs. So essentially every once in a while we would have a very, very large potential where the amplitude of the potential would be capital A, and this would be the functional form of our periodic square potential, provided that the B, the width of our potential is the potential well is extremely narrow. And now what we must do is that we must somehow calculate those Fourier coefficients that are associated with this specific type of a potential barrier. And they can be just calculated via the definition. So all of these Fourier coefficients, we can calculate them using the integral of 1 over a. This is the periodicity in our system, and we integrate over a single period over the function, and we have the function ux, and then we multiply that with the exponent igx. So this is basically the definition. How do we calculate those Fourier coefficients if we are making a Fourier series description of our function ux? And this is what we are doing here, of course. Now what we get out, we can plug in our form, the above form for the u, and then we have the capital A. We can take that out from the integral. The a's, they vanish, so 1 over a plus the times the a, they vanish, and we are left with the summation over m's of the Dirac delta functions and of the exponent igx's. And now, of course, while we are integrating over the first, or we of course could be integrating over any specific unit cell, but for simplicity we integrate now from 0 to a, so basically we can force the integer m to be 1, so that they only need to consider that single well in that single lattice unit cell. And then now we have something that we integrate a delta function of exponent, plane wave exponent minus igx. And of course we know what is the solution. So the delta function basically just picks out a given x value out of the integral. And then we are left in having a form where we have the a, the amplitude times exponent IgA. And now recall what is the form of the reciprocal lattice vector g. So that was of course 2 pi over small a. So we are left with an exponent where the a's vanish, and then we have exponent I 2 pi, and always that must be unity. So we are left with the not very interesting looking Fourier coefficients because they're always capital A's. But on the other hand, nice simple math like is very conceptually illustrative. So let's be happy with this outcome. So now we basically have just UGs, all of them for any G are just A's, and we can plug that into the central equation. And we will further come up with a shorthand notations that will simplify our notation and derivation. So let's just denote the kinetic energy term with the lambda k. So essentially lambda k equals h bar squared times k squared divided by 2m. And with this, the central equation can be written out in slightly cleaner way. So it will be lambda k minus e, the energy, times the Fourier coefficient associated with the wave function ck, plus a times summation over the wave function Fourier coefficients. And that's essentially what we will also come up with a shorthand notation for this summation. So I can just denote this to be fk, and that's essentially equal to f in k minus ng location. And this is now equals to 0. So this is already a lot simpler form for the central equation, so that this is already looks like solvable equation, I would say. And we proceed in solving this, and this is our central equation. And what we want to seek is that we want to know what are the ck's there, because once we know the ck's, then we can describe the wave function using the ck's, because that's then all the information we need to compose the wave function in the reciprocal space. So ck, essentially we can write that, we can solve the above equation with respect to the ck, and that will be equal to minus a times fk, so that's the summation over n's, and then on the denominator we have lambda k minus e. And this term fk can be cancelled out of this equation by essentially summing over this ck term. So essentially we sum both sides of the equation over n. So then we are left out with the ck minus ng on the left hand side, and then we are having a summation over indices. So a summation over n on the right hand side of terms minus a times fk divided by lambda k minus ng minus e. And sorry, I should have capital G here, so that's the normal reciprocal, that is vector G here, as in before, and same thing here. And now essentially like what we get is that we can write the fk, so this left hand side to be equal to fk. So as we noticed here, this is the shorthand notation, this kind of summation equals to fk. And also physically that must be equal to the fk minus ng, so that we will use later. But here this way we see that this left hand side we can just write that to be fk, and that's nice. Because when we do that, we see that we have on the left hand side we have fk, and on the right hand side we have fk, and then we can manage them, make them go away from that equation, and we have even slightly simpler form for the equation. So now the fk's vanish, so we have 1 over a turned onto the left hand side of the equation, that must be equal to minus sum over n of terms 1 over lambda k minus ng's minus e's. And now we can start wrapping this up into the kind of seeked form. So recall we used a simplification, so this lambda k, that was equal to the kinetic energy term, so that was the h bar squared times k squared divided by 2m, and then the energy, it's basically the kinetic energy, so it's h bar times k times 2m. And now both sides of the equation we can multiply them with the h bar squared divided by 2m, and then we result in an equation where on the left hand side we have h bar squared divided by 2 times m times capital A equals minus summation over n of 1 over k minus ng squared minus 2 times me over h bar squared. And now the below can be further simplified, so that's minus summation over n, and then we have 1 over k minus ng squared minus k squared. So please denote this essentially equals to k squared here, as seen here. So that this is essentially what we're using here. And now, one could, after really a little bit tedious bit of algebra, this is actually not entirely straightforward, and the above equation can be turned into the form that we wanted to have, because this is the form that we had already solved earlier. So then on the left hand side we are left having m times a, capital A times small a squared divided by 2h bar squared per ka times sine of ka plus cosine of ka, and on the right hand side we just have the cosine of small k times a. And when we set the amplitude of the sine wave to be p, then we see that we have the earlier dispersion relation. That was the transcendental equation that is not the easiest to plot anymore, but then can nevertheless be done with the help of the computers. So this is how things can be solved. And now we see that both results, how both ways of solving the Kronig Penney model end up with the same results. And I would just like to note to you that I probably will put this as a homework exercise, because I think it's an educating exercise, and it shows that in a textbook if sometimes somebody like Charles Kittle says that they after a tedious algebra, you get the result, what it might mean, this like a tedious bit of algebra, so that you know that next time like you would be able to do that kind of derivations. So I thank you for following me all the way down to the end of the Kronig Penney model, and you know now how you can build a dispersion relation for a nearly free electron. And what we will do next is that we will briefly outline to you how we could generalize this approach, and then finally we will conclude by actually taking use of this model and try to understand the electrical conductivities of metals. So essentially we will go into the transport properties of metals. So thanks for listening, and please stay tuned.